Okay, this chapter is dealing with temperature and heat. There is a difference between temperature and heat, and we'll talk about that now. Okay, temperature is a measure of the average translational kinetic energy per molecule in a substance, and it's measured in degrees Celsius or Fahrenheit in kelvins. What this means is, right, think of each of you as a molecule. You are mostly stationary, right? There's some little bit of vibration, there's some movement, but mostly you're stationary, which means that your temperature, if you were molecules, the temperature in this room is low. Now, if you guys were to start kind of randomly bopping around, right, kind of slowly, the temperature is going up. If I feed you a whole bunch of chocolate and you get like well, if you were third graders and I fed you a whole bunch of chocolate like I made the mistake of doing, and you get all like totally hyped up, then you'll be bouncing all over the walls, right? It'll probably take more than chocolate to get you guys all bouncing around, right? I probably shouldn't ask what would get you, right? I'm sorry? Oh, with enough chocolate you would bounce off the walls?
Yes,
okay.
I'll do whatever you want.
So, extra credit to you if you can videotape that, and right? Okay. So, third graders, don't do this. You feed them a bunch of chocolate before you start teaching them, they like bounce all over the place, right? And so that would be an example of a high temperature room, right? So, take the molecules, increase their kinetic energy, which means they're moving faster for each molecule, and the temperature is going up. The temperature is a measure of the average kinetic energy. So from this comes the concept of absolute zero. Absolute zero is the lowest, in terms of temperature, is the lowest possible temperature that a substance can have. Basically, all the molecules have their minimum kinetic energy. If it's possible, all of them are absolutely stationary. Not completely true, right? But to a first approximation, we can say all the molecules and atoms are stationary, so there's no translational kinetic energy. That gives us absolute zero. You've all seen this, a thermometer. Centigrade scale on the right, Fahrenheit scale on the left, right? Degree F versus degree C. And 0 degrees centigrade is the freezing point of water, right? Freeze water, it becomes ice. Put this thermometer on ice and you end up with 0 degrees as the reading. Now, you heat up the ice, it melts, it becomes water. You heat it up until it starts converting, it boils and converts to steam. The temperature which it's boiling is 100 degrees centigrade. The corresponding Fahrenheit scale is 212 degrees Fahrenheit, corresponding to the 100 degrees centigrade, and minus 32 Fahrenheit, corresponding to the 0 degrees centigrade. Right? Now, that's a rather strange scale. So I wondered where that came from, and here's a story that I heard. I have no idea whether it's true or not, that Fahrenheit, the guy who came up with that scale, at that time was looking for the most reproducibly, he was trying to create a temperature scale, and he wanted to have the lowest temperature that he could reproducibly create to calibrate the low end, and the temperature that he could reproducibly create to calibrate the high end, right? So what he did is that he used, if I recall correctly, he used ice with a bunch of salt in it or something, some particular kind that he could find, and he marked that temperature as 0. So that 0 turned out to be like minus 18 degrees centigrade. This is ice with salt that you can make it colder. Allegedly, this is the story. And what happens for the 100 degrees, he said 100 degrees at the point where the hottest thing that he could find was his wife. So he put the thermometer under her armpit, right? Isn't that funny? Like a multiple entendre, right? So that was the temperature of her armpit, or it may have been her tongue or something like that, right? So and he set that to 100, but now we realize that really her temperature was not 100. Her temperature must have been 98.6, but there's some experimental error. So that's the story as to why we ended up with such a weird scale, right? And later on, if I read, it may be the French who came along and created the Celsius scale and say, hey, let's take water and boil it or freeze it and use those two extremes. And actually that's a benefit because we don't have Fahrenheit's wife with us anymore. It's very hard. If everybody in the world had to calibrate the thermometers by Fahrenheit's wife, right? Yeah, she would be busy. She could charge a bunch for that. Okay, introducing the concept of internal energy. We all know what energy is, right? We all know that we don't know what energy is, but we assume that we know it's something that helps us to do things, right? We've been through that in the previous lecture. But since we said that, we know what energy is. Now, internal energy is energy that is?
Internal.
Good job. Extra credit. It's internal. So the sum of all the molecular energies, kinetic and potential, that are internal to a substance. So if you ask what is your internal energy, you add up all the energies inside you, and that's your internal energy, right? So all the energy is associated with the molecules. So this is an illustration. Here's a kid with a sparkler, right? The temperature of the sparks that are coming off of the sparkler is very high, about 2000 degrees centigrade. One of the sparks ends up on the kid's hand or arm, but it does not burn him. The reason why it doesn't burn him, even though the temperature is so high, is because the material in the spark is so little that the total internal energy is very small. So that small energy gets dissipated over his arm or over the skin that's in contact. And so per unit area, per unit cell, it's not that much energy. And so even though the temperature is high, the amount of energy is low. And so he doesn't.
I scar on my leg from where I sparked over.
I'm sorry. Exocredit to you. That's a sympathy exocredit. I don't pity you. There's a difference between pity and sympathy.
True.
Right? Okay, so introducing the concept of heat. Heat is the energy that flows from an object of higher temperature to the object of lower temperature. And it's measured in calories or joules. So it's energy flowing from one place to another. So just like this, here we've got this glass pipe. You pour water at this end, so the water gets higher on this end and it's lower here. The water flows from here to make this equal, right? Temperature does the same thing. If you were to have high temperature here and low temperature here, heat, would flow from here to here until the two of these equalize. Very similar to the water flowing. So illustrating the concept of heat versus temperature, right? Or energy, the total molecular kinetic energy. Here is a cup of really hot coffee, and here is a bucket of lukewarm water. The temperature of this bucket is higher or lower? Lower, right? Lukewarm versus like boiling hot, steaming hot, or boiling hot, or whatever. However, the total energy in this bucket can be greater than the energy here. Because it's bigger. So it's the equivalent of saying, let's say that, I'm not saying that she does, let's say that Jenna has $100 in her wallet, right? And let's say she does, right? If you want, I can. I'm just kidding. Okay, so $100 in her wallet. Let's say the rest of us only have $10 each. So Jenna has the highest temperature, right? The highest temperature, but her total energy, we as a whole, if all of us are in the other bucket, if you add up all our tens, we have a higher number than the 100. So we have more energy as a whole, which is the same effect going on here.
Then if kinetic energy determines what the temperature is, right? Because the higher the kinetic energy, the higher the temperature. Wouldn't the warm bucket of water burn you worse than the coffee?
Temperature is a measure of the same thing. The temperature is a measure of the is a measure of the average kinetic energy.
10 minutes of that. Okay.
I'm going to switch.